Welcome to our first session on numerical root finding. In this lesson, we will focus on the fundamental concepts of function zeros, how to identify them graphically, and the essential technique of bracketing. By the end of this part, you should be able to define what a root is and find it on a graph. You will also learn why we always plot functions before solving them numerically and how to implement the bisection and Brent methods. Root finding is a cornerstone of computational physics because many laws can be expressed as a function equal to zero. Whether you are finding when a projectile hits the ground or where net forces balance out, you are solving a root-finding problem. Mathematically, a root is simply an input value, r, that makes the function f of r equal to 0. Visually, this is the point where the function's curve either crosses or touches the x-axis. We start by importing our standard libraries. Before we let a computer hunt for a number, we should always visualize the function. Here, we define a fifth-order polynomial, x to the fifth minus x plus 1, and set up a range of values to plot so we can see its behavior. This continuation of the code handles the labels and the formatting for our plot. Adding a horizontal line at 0 is a crucial diagnostic step, as it provides a clear reference for where the roots might be located. Looking at the resulting graph, we see that the function crosses the x-axis somewhere between -2 and -1. This visual check confirms that a root exists in this region and gives us a starting point for numerical methods. To verify this more precisely, we can evaluate the function at the boundaries of our suspected region. We pick a equals -2 and b equals -1 to see if the signs of the function values are actually different. The output shows that at x equals -2, the function is negative, but at x equals -1, it is positive. Because the product of these values is negative, we have mathematically confirmed that a sign change occurs. This brings us to the intermediate value theorem. If a continuous function changes sign over an interval, there must be at least one root inside. We call this interval a bracket, and it provides a safe, bounded area for our search. However, be careful. A root can exist without a sign change if the function just touches the axis. For example, the parabola x minus 1 squared has a root at 1, but it stays positive on both sides. This code snippet sets up a plot for our touching root example. We are scatter plotting a point specifically at the root to show that even though the function never goes negative, it still reaches 0 exactly at x equals 1. In this plot, we clearly see the function dip down to touch the axis and then bounce back up. A simple sign change test would fail to find this root, which is why graphical inspection is such a powerful tool. The numerical output here confirms that the function values on either side of the root, at 0.5 and 1.5, are both positive. This demonstrates why bracketing methods require extra care when dealing with even-powered roots. Another challenge arises when an interval contains multiple roots. For a trigonometric function like sine, a wide interval might contain several zeros. A sign change only guarantees that at least one root exists, not that there is only one. This plot of the sine function illustrates the point. If we chose a bracket from -6 to 6, we would find a sign change, but we would also be skipping over several other roots in between. The bisection method is the most robust way to find a root once we have a sign-changing bracket. We begin by defining a function that takes the target function, the endpoints of the bracket, and a desired tolerance. Inside the loop, the algorithm calculates the midpoint and checks the sign. By determining which half of the current interval still has a sign change, we can throw away the other half and systematically narrow our search. The process repeats until the interval is smaller than our tolerance, or we reach a maximum number of iterations. If the function does not find a root within those limits, we raise an error to indicate it did not converge. Here, we apply our bisection function to the polynomial we looked at earlier. It successfully finds the root at approximately -1.167, requiring 34 iterations to reach a very high level of precision. To understand how the interval shrinks, we can print out the history of the iterations. This code block will display the first 8 steps, showing the boundaries A and B closing in on the root. In this table, you can see the midpoint jumping back and forth as it narrows the bracket. Each step cuts the search area exactly in half, which is why the method is so reliable even if it is not the fastest. Now we will visualize the result. We use a scatter plot to place a marker at the specific root coordinates identified by our bisection algorithm, overlaying it on our original function plot. The plot confirms our numerical result. The bisection root marker sits exactly where the curve intersects the dashed line representing the x-axis, giving us confidence in the accuracy of our calculation. While bisection is great, professional libraries like SciPy offer optimized solvers. The BrentQ function is generally the preferred choice for bracketed root finding because it combines bisection with faster interpolation methods. The results from BrentQ match our bisection root almost perfectly, but with even higher precision. Comparing the two shows that the difference is negligible for most physics applications, but Brent's method usually converges in fewer steps. Let us apply this to a real physics problem. Calculating when a projectile launched from a height of 1.5 meters at 12 meters per second will hit the ground. We define the kinematic equation for height as our function. Before solving, we generate a plot of the height over time. We are looking for the point where the projectile's height returns to 0, which represents the moment of impact with the ground. The trajectory shows that the projectile goes up and then falls, crossing the ground level between 2.5 and 3 seconds. This gives us a clear bracket for our root finding algorithm. We use BrentQ to find the root within the bracket of 2 to 3 seconds. This will give us the precise impact time, and we will check the height at that time to ensure it is effectively 0. The calculation tells us the projectile hits the ground at approximately 2.57 seconds. The height at this time is nearly 0, within the limits of machine precision, confirming the solve was successful. Finally, we update our plot to show the impact time explicitly. Highlighting the root on the physical trajectory helps us verify that the mathematical solution makes sense within the context of the physics. The dot on the graph marks the exact end of the flight. By using root finding, we have transformed a visual estimate into a precise physical prediction that we could use for further analysis or design. Now it is your turn. Try defining a practice function like cosine of x minus x. Use both plotting and a numerical solver to find where these two terms balance each other out. Your results for the practice function should show a root near 0.739. This is a classic transcendental equation that cannot be solved with basic algebra, making it perfect for numerical root finding. In summary, we have seen that roots are the foundation of many physics solutions. By using bracketing and bisection, we can reliably find these points. In our next lesson, we will look at even faster methods that use initial guesses instead of brackets.